Hello everyone, in this video I am going to make a video for visually impaired student from the book Pradeep's Organic Chemistry, chapter name Spectroscopy Nuclear Magnetic Resonance. Introduction. During the last 6 decades or so, spectroscopy methods such as ultraviolet, infrared, nuclear magnetic resonance, and mass spectrometry have emerged as powerful tools for identification and structure determination of organic molecules. The ultraviolet and infrared spectroscopies have already been discussed in detail. Therefore, in this unit, we will discuss nuclear magnetic resonance spectroscopy, which was discovered by Felix Bloch and Edward Purcell in 1946. The field of NMR spectroscopy has been further divided into number of subfields depending upon the magnetic nucleus being examined. For example, proton magnetic resonance (PMR) or 1H NMR, carbon magnetic resonance 13 carbon NMR, fluorine magnetic resonance 19 fluorine NMR, phosphorus magnetic resonance 31 phosphorus NMR, etc. However, in this unit we will discuss only proton magnetic resonance and the basis principle of NMR spectroscopy. Magnetic properties of nuclei. Like electrons, the nuclear particles, that is protons and neutrons, are also considered to spin about their axis. Further, like electron, each proton and neutron has a spin quantum number of 1 by 2. If the protons and neutrons in a nucleus are not paired, the nucleus as a whole will have a resultant nuclear spin 1. The numerical values of this nuclear spin quantum number 1 depends upon the number of protons and neutrons having parallel and antiparallel spins. In agreement with the above general rules, nuclear such as 1 hydrogen 1 proton, 3 hydrogen 1, 13 carbon 6, 15 nitrogen 7, 19 fluorine 9, 31 phosphorus 15, etc. all have I is equal to 1 by 2. 11 boron 5, 23 sodium 11, 35 chlorine 17, 79 bromine 35, 81 bromine 35, etc. have I is equal to 3 by T. 2 and 17 oxygen 8 has been found to have I is equal to 5 by 2. Nuclei such as 4 helium 2, 12 carbon 6, 16 oxygen 8, 32 sulfur 16 all have I is equal to 0. It is fortunate for organic chemists that 12 carbon 6 and 16 oxygen 8 are non-magnetic, otherwise the NMR spectra of organic molecules would have been much more complex. Nuclei such as 2 hydrogen 1 deuterium and 14 nitrogen 7 have I is equal to 1, while 10 boron 5 has I is equal to 3. Now, since atomic nucleus is associated with the charge, therefore like any other rotating charge, it generates a magnetic field along the axis of its spin. Therefore, such a nucleus behaves as a tiny bar magnet and has a characteristic magnetic moment mu. Nuclear spin states. When a nucleus with I greater than 0 is placed in an external magnetic field, it is found to have a set of discrete orientations with respect to the applied magnetic field. These various orientations are referred to as the spin states. For a nucleus with the spin quantum number I greater than 0, there are 2I plus 1 allowed spin states which differ from one another by unity. That is, the various spin states are given by minus I plus 1, and so on, I minus 1 plus I. Thus, it follows that nuclear spin states like electronic and vibrational states are quantized. For example, a proton hydrogen nucleus with I is equal to 1 by 2 has two allowed spin states, 2 1 by 2 plus 1 is equal to 2, designated as minus half and plus half. For chlorine with I is equal to 3 by 2, there are 4 allowed spin states, 2 into 3 by 2 plus 1 is equal to 4, designated as minus 3 by 2 plus 1 by 2. minus half and plus 3 by 2. In the absence of a strong external magnetic field, the nuclear spins of a magnetic nuclei are oriented randomly. However, when these magnetic nuclei are placed between the poles of a strong magnet, they either align with the field or opposite to the field. When a compound containing hydrogens is placed in an applied external magnetic field, the protons may assume one of the two possible orientations with respect to external magnetic field. These two possible orientations do not have the same energy and hence are not equally populated. The orientation in which the spins of the other nuclear magnets are aligned parallel, I is equal to plus half to the external magnetic field, is slightly lower in energy, and hence this spin state is slightly favored over the other orientation, I is equal to minus half, in which the spins of the nuclear magnets are aligned anti-parallel to the external magnetic field. The difference in energy between the two spin states is designated as delta E. In general, the value of delta E is very small, but the magnitude depends upon the strength of the applied magnetic field. From figure 2.3, it is clear that when H naught is equal to 0, delta E is equal to 0, that is, in the absence of a magnetic field, the two spin states of a proton have equal energy. However, as the strength of the applied field increases, the energy difference between the two states increases. At a field strength of 14,200 gram g or 1.41 T, delta E is equal to 2.39 into 10 to the power minus 5 kilojoule mole inverse, while when H naught is equal to 23,500 G or 2.35 T, delta E is equal to 3.97 into 10 to the power minus 5 kilojoule mole inverse, whereas G is equal to Gauss and T is equal to Tesla are units of magnetic field in CGS and SI units respectively. Further, 1T is equal to 10 to the power 4 Gauss. Principle of nuclear magnetic resonance. To understand the principle of nuclear magnetic resonance, let us consider the motion of a common spinning top. When the spinning top is disturbed a little, its spinning axis will trace out a circle perpendicular to the Earth's gravitational field. Such a motion is called precession. In a similar way, when a nuclear magnet is placed in an external magnetic field, it will experience a torque force perpendicular to the axis of the nuclear magnet, which will tend to align it with the field. Since the nuclear magnet is spinning, it will not align with the external magnetic field but will precess around it with a certain angular frequency omega, called the precessional frequency or the Larmor frequency. The frequency at which a proton will precess will depend upon the strength of the applied magnetic field. Stronger the applied field, higher is the precessional frequency. For a proton, if the applied magnetic field is 14,100 Gauss, the professional frequency will be 16 megahertz, 16 million cycles per second. Since a proton has two allowed spin state, I is equal to plus half and I is equal to minus half, it can precess in two principal orientations, one allied with the applied field low energy and the other opposed to the applied field high energy. It is possible to induce transitions between these two orientations by irradiating the precessing nuclei protons with the radio waves electromagnetic radiations of a correct frequency. When the precessional frequency of the nucleus proton is exactly equal to the frequency of the electromagnetic radiations, the absorptions occurs and the nuclear in lower energy spin state flip to the higher energy spin state. When this occurs, the nucleus and the radio frequency RF beam are said to be in resonance, and since this resonance is due to magnetic properties of the nuclei, it is called nuclear magnetic resonance and abbreviated as NMR. The exact amount of the radio frequency energy needed for resonance depends upon the strength of the external magnetic field and on the nucleus being irradiated. That is, delta E is equal to HV is equal to gamma H by 2 pi dot H naught, where delta E is equal to energy difference between the two spin states H is equal to Planck's constant, Y is equal to gyromagnetic ratio. It is the ratio of magnetic movement to angular movement and is constant for each nucleus. For a proton, the value of gamma is equal to 26,750. It may, however, be noted here that an NMR instrument with a magnetic field strength of 1.41 T and operating at a constant RF of 60 MHz can induce transition only among proton spin states in a molecule and is not useful for other nuclei. Therefore, separate instruments are required to observe transitions in the nuclei of other elements such as carbon, phosphorus, fluorine, etc. However, the modern, more expensive Fourier transform FT instruments, which are commonly used these days, can be used to observe the resonance of nuclei of several different elements in a single instrument. Instruments with the 200 and 300 MHz are now quite common, and instruments with a frequency up to 800 MHz are found in the advanced research institutions and bigger universities. We have discussed above that the energy difference between the two spin states of a proton at 60 MHz is just 2.39 into 10 to the power minus kilojoule mole inverse. Since this energy difference is too small, thermal energy due to room temperature is sufficient to populate both the spin states. There is, however, a slight excess of nuclei in the lower energy spin state. The magnitude of this difference can be calculated by using Boltzmann distribution equations. The following equation gives the Boltzmann ratio of nuclear spins in the upper and lower state. N upper upon N lower is equal to E minus delta E upon KT is equal to E minus HV upon KT, where delta E is the energy difference between the upper and the lower spin state and K is the molecular, not molar gas constant. Using this equation, we can calculate that at 298 Kelvin for an instrument operating at 60 MHz, there are 1,000,009 nuclei in the lower spin state for 1,000,000 that occupy the upper spin state. In other words, in approx 2 million nuclei, there are only 9 more nuclei in the lower state. These excess nuclei are the ones which are responsible for the NMR signals. When the 16 MHz radiation is applied, it not only induces transitions upward but also stimulates transitions downward. When the populations of the two states become exactly equal, we observe no net signals. This situation is called saturation. Therefore, while performing an NMR experiment, care must be taken to avoid saturation. Saturation is achieved quickly if the power of the RF signal is very high. If we increase the operating frequency of the NMR instrument, the energy difference between the two spin state increases, which causes increase in excess population. Example: 16 at 100 MHz, 32 at 200 MHz, 48 at 300 MHz, and 96 at 600 MHz. In another word, at high operating frequency 200 MHz, 300 MHz, 600 MHz, etc., more nuclei can undergo transition. Therefore, the sensitivity of the instrument increases and the resonance signals are stronger. PMR spectrum or origin of signal. In principle, a PMR spectrum can be obtained by placing the substance containing hydrogen nuclei or protons in a magnetic field of a constant strength and passing electromagnetic radiations of varying frequency through the substance and observe the frequency at which radiation is absorbed. In practice, however, it has been found more convenient to keep the frequency of the electromagnetic radiation constant and vary the strength of the magnetic field. At some value of the field strength, the energy required to spin the proton matches the energy of the EMR radiations. At this stage, absorption occurs and a signal is observed. Such a spectrum is called a PMR spectrum. The PMR spectrum is a plot of intensity of absorption along y-axis against magnetic field strength along x-axis. By convention, magnetic field strength increases from left to right across the chart. Since the magnetic field strength and the frequency are related by the equation V is equal to mu h naught upon hi is equal to lambda h naught upon 2 pi. The position of any absorption signals along the x-axis can be expressed in either field or the frequency units. A typical NMR absorption is shown. We have discussed above that a PMR signal is obtained at some value of the field strength at which the energy required to flip the proton become equal to the energy of the EMR radiation. Therefore, we may expect that all the protons in an organic molecule will absorb at exactly the same field strength. Consequently, the PMR spectrum would consist of a single signal and it will be of little use to organic chemistry. In practice, it has been found that all the protons do not absorb at the same frequency. This is due to the reason that the frequency at which a proton absorbs depend upon the magnetic field which that proton actually feels, and this effective field strength is not exactly the same as the applied magnetic field. This effective field strength which a proton feels depend upon its local environment, that is electron density around that proton and the presence of other protons in its neighborhood. In other words, each proton, or more precisely, each set of equivalent protons will have slightly different environment than every other set of equivalent protons and hence will absorb a slightly different applied field strength to experience the same effective field strength at which the absorption occurs. Thus, it follows that a given radio frequency, the protons having different environment experience the same effective field strength but absorbs a different applied field strength. Since in a PMR spectrum absorption is plotted against the applied field strength, a PMR spectrum will consist a number of absorption signals which would be very useful in determining the structure of molecules. NMR spectrometer. We have discussed above that there are two ways to scan an NMR spectrum, either by keeping the magnetic field H naught constant and changing the frequency of the radio frequency oscillator, or by keeping the frequency of the radio frequency oscillator constant and changing the magnetic field. In practice, however, NMR instruments which work at constant radio frequency are used since they are easier and cheaper to construct. Such instruments are called continuous waves or CW spectrometers. A systematic diagram of an CW NMR spectrometer is shown in figure. It consists of the following parts: a powerful electromagnet whose strength can be varied, a radio frequency generator, a detector which monitors the absorption of energy and amplifies the electronic signals, a recorder which records the spectrum on a chart paper which is calibrated in frequency and ppm units, a 5 mm wide long sample tube. The sample is dissolved in a suitable solvent which does not contain proton, usually CCl4, and is spun around its axis to ensure that all parts of the solution experience a relatively uniform magnetic field. In between the poles of a magnet there is a coil which is attached to a 60 MHz RF generator. This coil supplies the electromagnetic energy used to change the spin orientations of the protons. Perpendicular to the RF oscillator coil is a detector coil. More advanced NMR spectrometers known as Fourier transform NMR spectrometers are known available. In these instruments, magnetic field is held constant and the radio frequency is varied. While a CW spectrometer takes 5 minutes to scan the PMR spectrum, FT-NMR instrument can record a spectrum within 5 seconds. Solvents used in PMR spectroscopy. Any solvents which does not contain protons can be used in PMR spectroscopy. The most widely used solvent is deuterated chloroform. Other solvents which are commonly used in PMR spectroscopy are carbon tetrachloride, deuterated acetone, deuterated dimethyl sulfoxide, deuterated benzene, etc. Trifluoroacetic acid is also used sometimes even though it contains a proton. The reason being that this acidic protons absorbed at a very low field, hence does not interfere with the absorption of most of the compound which usually occur in the range 0 to 10 delta. Number of NMR signals, equivalent and non-equivalent protons. We have discussed above that in a given molecule's proton with a different environment absorbs at different field strength, while proton which have the same environment absorbed at the same applied field strength. A set of protons are said to be equivalent if they have the same environment and non-equivalent if they have different environment. Since each set of equivalent protons produces the different signals, therefore the number of signals in an NMR spectrum tells us to how many different sets of equivalent protons or how many different types of protons are present in a given molecule. In most of the cases, it is possible to predict the different types of proton present in a given molecule simply by looking at the structure, but this is not always easy. Therefore, we must devise a method by which we can accurately tell us how many different kinds of protons are present in a molecule. In this method, we imagine that each of the hydrogen atoms or proton is substituted by some other atom's Z. The substitutions of either of the two protons by Z gives either the same or enantiomeric product. The two protons are chemically equivalent, otherwise not. It may be noted that in general, chemically equivalent protons are also magnetically equivalent and thus give rise to the same signal in PMR spectrum. Now, let us illustrate this method by considering a few examples. The molecules of ethyl chlorides contain 3 methyl and 2 methylene protons. Replacement of a methyl protons would give ZCH2, CH2Cl, and replacement of a methylene proton will give CH3, CHZ, HCl. These are obviously different products. Therefore, methyl protons are not equivalent to methylene protons. However, it may be noted that the 3 methyl protons are equivalent amongst themselves since the replacement of any of them gives the same product ZCH2, CH2Cl. On the other hand, replacement of either of the two methylene products would give one of the two enantiomeric products. Such pairs of products are called enantiotopic protons. The environment of these two protons are mirror images of each other and hence are magnetically equivalent to each other and thus give rise to one signal if the PMR spectrum is scanned in an achiral solvent. However, in a chiral solvent, the two products would become magnetically non-equivalent and would give two signals. From the above discussion, it follows that ethylene chloride contains only two types of proton and thus gives two PMR signals. Proceeding on similar lines, we can easily predict the number of different types of protons present in the following molecules. Let us now consider a molecule of 2-bromopropene. It has 3 methyl and 2 vinylic protons. The 3 methyl protons are obviously equivalent among themselves since replacement of each one of them gives the same product. On the other hand, replacement of either of the vinylic protons produces one of a pair of diastereomeric product. Such pairs of protons are called diastereotopic protons. The environment of these two protons are neither identical nor mirror images of each other and hence are non-equivalent. As such, each of these would give us separated PMR signals. Thus, 2-bromopropene contains 3 kinds of protons and hence gives 3 NMR signals. Similarly, in 1,2-dichloropropane, the two protons are C1 diastereotopic and thus give rise to separate signals. Thus, the molecules of 1,2-dichloropropane in all gives 4 PMR signals. Proceeding on similar lines, we can easily predict the number of different types of protons in the following molecules. Positions of signal shielding and deshielding. We have discussed above the number of signals in a PMR spectrum tell us how many different types of protons are present in a given molecule. In a similar way, the positions of signals tell us what kind of protons they are. In other words, the position of signals tell us the actual environment of the various protons and thus indicates the nature of protons, that is, whether the protons are aliphatic, aromatic, vinylic, acetylene, or are adjacent to heteroatoms such as oxygen, nitrogen, sulfur, halogens, etc. When a molecule is placed in a magnetic field to get its PMR spectrum, the applied magnetic field causes the circulations of electrons surrounding the protons. The circulations of electrons produces a secondary magnetic field called the induced magnetic field. This induced magnetic field may either oppose or reinforce the applied magnetic field. For example, circulations of electrons in Sigma bonds surrounding the protons generate an induced field which opposes the applied magnetic field. On the other hand, circulations of electrons, particularly the pi electron, generates an induced magnetic field which may either oppose or reinforce the applied field acting upon a protons depending upon its location in the induced field. For example, circulation of pi electrons in benzene derivative products. This is an induced field which reinforces the applied fields at proton. Similarly, circulation of pi electrons of the CH double bond O group of reinforces the applied field at the proton. In contrast, the circulations of pi electrons of acetylene produced an induced field which opposes the applied field at the proton. When the induced field opposes the applied field, the actual field acting on the proton decreases and the proton is said to be shielded. In order to get an absorption signals from the shielded protons, the applied field has to be increased somewhat to reach the same effective field strength at which the absorption occurs. The shielding shifts the absorption upfield. On the other hand, when the induced field reinforces the applied field, actual field acting on the proton increases and the proton is said to be deshielded. Obviously, to get an absorption signals from a deshielded protons, the applied magnetic field is to be decreased somewhat so as to achieve the same effective field strength at which absorption occurs. The deshielding shifts the absorption downfield. For example, the induced field opposes the applied field at the protons of acetylene while it reinforces the applied field at the protons of benzene. As a result, acetylenic protons are shielded and absorbed upfield, whereas benzene protons are deshielded and absorbed downfield. Chemical shift. The shift in the position of PMR signals resulting through shielding and deshielding by circulation of electrons in chemical bonds is called the chemical shift. Proton in most of the usual types of organic compounds absorb over a range of 700 Hz at a field strength of 14,100 Gauss. At this field strength, protons absorb at a frequency of 60 into 10 to the power 6 Hz. The shielding and deshielding of protons by electrons produce very small changes, 1 in 10^8 in the strength of the applied magnetic field. These small changes in the magnetic field strength cannot be determined accurately. Consequently, the absolute position of the PMR signals cannot be obtained from the instrument as in the case with UV and IR spectrometers. However, relative protons frequencies can be readily determined with an accuracy of about 1 Hz. Therefore, chemical shift protons are expressed in Hz or CPS with reference to a particular standard. It may be noted here that even though the chemical shifts are expressed in Hz, it does not mean that the frequency of the electromagnetic radiations is being varied. In actual practice, it is the magnetic field which is varied. Since the frequency and the strength of the magnetic field are related by the equation V is equal to gamma H naught upon 2 pi, the frequency units are justified. The most commonly used reference for PMR spectroscopy is tetramethylsilane. It is chosen as a reference compound for the following several reasons. It has 12 magnetically equivalent protons. Therefore, a very small amount of TMS produces a relatively large single sharp signal. TMS protons absorbed at a field much higher than the protons in most of the usual organic compounds. This is due to the reason that silicon is more electropositive than carbon. It thus pushes electrons into the methyl groups of TMS by its plus I effect. As a result, the protons of carbon-hydrogen bonds in TMS have high electron density around them and hence are highly shielded. It is chemically inert and is also called highly volatile. Therefore, after the spectrum has been scanned, the precious samples can be recovered by the removal of TMS by evaporation. It is highly miscible with most of the organic solvents. Units of chemical shift. We have shifted above that the chemical shifts are expressed in Hz as the difference in the frequencies of absorption of a particular proton and the organic compound and the product of the reference compound. But we know that the chemical shift is proportional to the strength of a different oscillator radio frequency such as 40, 60, 100, 200 megahertz. It is desirable to express the chemical shift in some unit which is independent of the field strength. The most commonly applied units in parts per million of the oscillator frequency. To do this, the chemical shift in hertz is multiplied by a factor of 10 to the power 6 and then divided by the oscillator frequency of the instrument. For example, the protons of acetone absorbs at 126 Hz downfield from TMS at 60 MHz. Its chemical shift is equal to 2.1 part per million. However, if the spectrum of acetone is scanned at 100 MHz, the proton will absorb at 210 Hz downfield from TMS, but its chemical shift will still be 2.1 part per million. It may be noted here that the factor 10 to the power 6 is included in the numerator, simplified for convenience to avoid the fractional values. From the above discussion, it follows that the chemical shift when reported in part per millions are dimensionless and are independent of the field strength or the oscillator frequency of the instrument. Therefore, they are simply a function of the chemical environment of the protons in the given organic molecules. Scales of the chemical shift in terms of part per million. The chemical shift are expressed in the following two scales. First, the delta scale, where delta is equal to delta V in hertz into 10 to the power 6 upon my oscillator frequency. Then tau scale, where tau is equal to 10 minus delta. On the delta scale, the position of TMS scale is taken as 0.0 part per million, and most of the chemical shift have delta values between 0 to 10. A small delta value indicates a small downfield shift, with a large delta value has a large downfield shift. In other words, shielded protons have delta values, whereas de-shielded protons have large. On the tau scales, the position of the TMS signals is assigned a value of 10 part per million, and most chemical shifts have values between 0 to 10. Here, a small tau value refers to an absorption at low field, and a high tau values indicates a high field absorption. In other words, shielded protons have high tau values, whereas de-shielded protons have low tau values. It may be noted here that some compounds have protons which are even more shielded than of the TMS. Their chemical shifts are assigned either negative delta values or more 10 tau values. Chemical shifts of different types of protons. We know that the chemical shift of a protons depend upon its electronic environment. In a given molecule, protons with the same environment, that is equivalent protons, have a same chemical shift, while proton in different environment, that is non-equivalent protons, have different chemical shifts. In another word, a proton with a particular environment will have almost the same chemical shift regardless of the molecules in which it occurs. Therefore, from the positions of the signals in an PMR spectrum of a sample, we can safely tell as to what is electronic environment of each type of protons in that sample. The chemical shifts of different kinds of protons related to TMS are given in a table. It should be noted that the chemical shift given for each type of proton may show a slight variation, since the chemical shift of a proton also depends to some extent on the overall structure of the molecule, solvent, temperature, and concentration of the sample used for scanning the PMR spectrum. Factors affecting chemical shifts. Some of the important factors which influence the proton chemical shifts are inductive effects, anisotropic effects, and hydrogen bonding. Inductive effects. The proton's chemical shifts increase as the electronegativity of the atom attached to the carbon atom bearing hydrogen increases. This is due to the reason that -I effect of the electronegative atom decreases the electron density around the proton, which causes de-shielding. Thus, higher the electronegativity, higher the de-shielding, and higher the delta value of the chemical shift. Further, greater the number of the halogen atoms, greater in the de-shielding. As the distance of the protons from the halogen increases, the de-shielding also decreases. Anisotropic effects. We have discussed in section 2.8 that the circulation of pi electrons may either shield or de-shield the protons depending upon its location around the pi electrons. Such effects, which depend upon the orientation of the proton relative to the induced fields, are called anisotropic effect. Thus, mainly due to anisotropic effect and partially due to sp2 hybridizations, the olefinic and aromatic protons are much more de-shielded than protons on a sp3 hybridized carbon. Aldehydic protons are also attached to sp2 carbons appears even further downfield than aromatic protons, mainly due to anisotropic effect and partially due to -I effect of the electronegative oxygen atom, which further reduces the electron density around the proton. Hydrogen bonding. Protons which exhibit hydrogen bonding show variable absorption positions over a wide range, since hydrogen bonding decreases the electron density in the oxygen hydrogen bond. Therefore, the protons involved in hydrogen bonding gets de-shielded. Further, stronger the hydrogen bond, more de-shielded is the proton. The extent of hydrogen bonding, however, depends upon the concentration, temperature, and nature of the solvent. Thus, in concentrated solution, hydrogen bonding predominates and hydrogen bonded protons appears in the range of 4 to the 5 delta. But at high dilution, hydrogen bonding does not occur and the oxygen hydrogen protons absorbs in the range 0 to 0.5 to 1.0. Important generalization. On the basis of the above discussion, the following important generalization can be made regarding the molecular structures and chemical shifts. Electronegativity atoms such as oxygen, nitrogen, and halogens de-shield the proton and the absorption shift downfield. Conversely, electropositive atoms such as silicon increases the electron density around the proton. As a result, proton gets shielded and the absorption shifts upfield. The sigma electrons of the carbon-carbon bond de-shields the proton attached to it. Thus, a 3-degree hydrogen is more de-shielded than a 2-degree hydrogen, which in turn is more de-shielded than a 1-degree hydrogen. However, hydrogen attached to carbon in the highly strained cyclopropane ring absorbs at the highest field around 0.5 delta. The chemical shift in delta value decreases. Due to anisotropic effect, the pi electrons of aromatic, olefinic, and C double bond O bonds have strong de-shielding effect on the attached protons. Due to strong electron withdrawing effect, the carbonyl de-shields the protons on the alpha carbon. Similarly, benzylic and allylic protons are de-shielded relative to protons on saturated carbon atoms. Hydrogen bonding de-shields the protons. In carboxylic acid, due to resonance and strong -I effect of the oxygen atoms, the electron density around hydrogen decreases significantly, and thus the proton of the oxygen hydrogen group of acids get highly de-shielded and thus absorbs in the region 10 to the power 5 to 12. Peak area and proton counting. We have discussed above that the number of signals in the PMR spectrum of an organic compound tell us to how many different kinds of equivalent protons are present in the positions, or chemical shift tell us as to what type of protons each signal represents. Besides this, it is also possible to determine the number of protons giving rise to particular signals by measuring the relative intensities of the signals. The intensity of a PMR signals means the area under that absorption peak and not merely the height of the peak. Further, the area under a particular peak is directly proportional to the number of equivalent protons giving rise to that signals. In other words, the relative areas under the different peak gives the relative number of protons of different kinds present in a molecule of the given compound. The peak area different signals in a PMR spectrum are measured by an electronic integrator, and the process is called integrations. The integration of signals are shown on the chart in the form of a stepped up curve called integral curve. The height of the steps are then proportional to the peak areas. Since the NMR chart paper is generally cross-hatched, we can easily calculate the height of steps by simply counting the number of squares. The relative peak areas are then converted into a simple whole number ratio by dividing each area by the lowest area. The ratio of some simple multiple of it gives the exact number of protons of each kind present in the molecule. Consider, for example, the spectrum of toluene. The spectrum contains two peaks, one at delta 2.32 due to methyl protons and other at delta 7.17 due to aromatic protons. The ratio of squares is 6:10 or 3:5. Thus, the actual number of methyl and proton is 3 and 5 respectively. Splitting of signals, spin-spin coupling. We have discussed above that the number of signals in a PMR spectrum is equal to the number of different types of protons present in the molecules. In another word, every set of equivalent protons gives one PMR signal. This is of course true for some molecules, but the PMR spectrum of most of the organic compounds are much more complicated than we expect. In view of the above statement, to illustrate this, let us consider the PMR spectrum of 1,2-tribromomethane. This compound contains two kinds of proton and hence its PMR spectrum is expected to show only two peaks, but its actual PMR spectrum shows as many as 5 peaks. Similarly, the PMR spectrum of 1,1-dibromoethane shows 6 instead of 2, and that of ethyl bramides contains 7 instead of 2 peaks. Consequently, the tertiary proton fills any one of the three fields, and hence the signal is split into three equally spaced peaks called a triplet. The relative intensities of the three peaks in this triplet are 1:2:1. That is, the central peak will be almost double in intensity than the other peaks due to combined probability of the two equivalent combinations. It is interesting to know that the spacing between the two peaks of the doublet is exactly the same as the spacing between any two adjacent peaks of the triplet. This is due to the reason that spin-spin coupling is a reciprocal process and the coupled protons affect each other to the same extent. This spacing in hertz is called the coupling constant. In the light of the above arguments, the PMR spectrum of 1,2-tribromomethane consists of one doublet due to the protons on C2 and one triplet due to the proton on C1. Further integration has revealed that the total area under the doublet is twice the area under the triplet, indicating that the double is due to two protons and the triplet is due to one proton. Let us now consider a system of two adjacent carbon atoms, one carrying three primary protons and the other one tertiary proton. We have discussed above the PMR signal is split into a doublet by one nearby proton and into a triplet by two equivalent nearby protons. Working on similar line, we can safely predict that three equivalent easily seen that there are 8 possible combinations of the spin state of 3 primary protons. However, there are 2 sets of 3 equivalent combinations. Therefore, there are not only 4 effective combinations. Consequently, the tertiary protons fills only one of these 4 fields at any moment. Therefore, the tertiary proton signal is split up into 4 equally spaced peaks called the quartet. Similarly, we can predict that the signal due to three primary protons will be split into 1:1 doublet by the one nearby tertiary proton. In the light of the above arguments, the PMR spectrum of ethylene bromide consists of a 1:1 doublet due to C2 protons as 1:3:3:1 quartet due to C1 protons. Further integration has revealed that the total area under the doublet is 3 times the area under the quartet, indicated thereby that the doublet is due to 3 equivalent protons and the quartet is due to 1 proton only. Lastly, let us consider the molecule of ethyl bromide. Its PMR spectrum, as expected, shows a 1:3:3:1 quartet due to 2 equivalent methylene proton and a 1:2:1 triplet due to 3 equivalent methylene protons. Since the 2 protons on the carbon atom carrying the bromine atoms are de-shielded due to -I effect of the bromine atom, the 2 proton quartet will appear at a lower field than the 3 proton triplet. In actual practice, it has been found to be so. That is, the 3 that their portion triplet absorbs at delta 1.67 while the 2 proton quartet absorbs at delta 3.4. Here again it will be found that the area under the triplet is 1.5 times the area under the quartet, indicating thereby that the triplet is due to 3 equivalent protons and the quartet is due to 2 equivalent protons. Rule for spin-spin splitting of a proton signals. In general, the following rules are quite helpful in predicting the spin-spin splitting of proton signals. First, splitting of a proton signals is only caused by non-equivalent neighboring or vicinal protons, that is protons on the adjacent carbon atoms. By non-equivalent protons we mean protons which have different chemical shifts. For example, the PMR spectrum of ethylene dichloride does not show splitting of proton signal since the vicinal protons are equivalent to one another. Splitting of one proton by another proton on the same carbon, that is geminal coupling, is seen only when the two geminal protons are non-equivalent. For example, we do not observe splitting because two vinyl protons of isobutylene since these are equivalent. On the other hand, we do observe the splitting between the two vinyl protons of two bromopropenes since they are non-equivalent. Further, the mutual splitting of protons separated by more than two atoms is normally not observed. For example, in the compound 1,2-dibromo-2-methylpropane, we do not observe splitting between 6 methyl protons on one hand and 2 CH2 protons on the other hand. For similar reasons, we do not see coupling between the ring and side chain proton in alkyl benzenes. The number of peaks into which a given proton signal is split in equal to one or more than the number of vicinal protons. In another word, the multiplicity of a proton signal is given by n plus n, where n is the number of vicinal protons. This is also called the n plus 1 rule. Thus, the PMI signal is split into a doublet peak intensities 1:1, one vicinal proton into a triplet peak intensities 1:2:1 by two vicinal protons into a quartet peak intensities 1:3:3:1 by three vicinal protons into a quartet peak intensities 1:4:6:4:1 by 4 vicinal protons and so on. In general, these relative intensities of the various peaks of a multiplet correspond to the coefficient in the binomial expansion 1 plus x power n, where n is the number of vicinal protons. For n is equal to 1, 1 plus x power 1 is equal to 1 plus x. The relative intensities of the doublet is 1:1. For n is equal to 2, 1 plus x power square is equal to 1 plus 2x plus x square. Thus, the three lines of the triplet have relative intensities of 1:2:1. These relative intensities of the components of a multiplet can be easily remembered by the Pascal triangle. All the peaks of a given multiplet, doublet, triplet, quartet, etc. do not have exactly the same intensities as predicted above. In general, it has been found that the inner peaks, that is, the peaks nearer the other coupled multiples, are larger than the outer peaks. For example, the doublet and the triplet in the PMR spectrum of 1,1,2 tribromomethanes are expected to be symmetrical but are actually not symmetrical. Similarly, the quartet and doublet in the spectrum of ethylidene bromide should be shown but are observed. Likewise, the quartet and the triplet in ethyl bromide should be seen but are actually observed. Perfectly symmetrical intensities are observed only when the separation between multiplets is very large than the separation within the multiplets, that is, when the chemical shift to difference is much larger, greater than 10 times than the coupling constant. The distance between the adjacent peaks in a multiplet is called the coupling constant. It is a quantitative measure of the effectiveness of spin-spin coupling. It is denoted by the symbol J, and the coupling constant between two protons marked HA and HB is represented as JAB. The value of the coupling constant is expressed in hertz or cycles per second. Unlike the numerical value of the chemical shifts expressed in hertz, the numerical value of J expressed in hertz is independent of the applied field strength but depends only upon the molecular structure. Therefore, coupling constant measures on a 60 MHz NMR instrument will be same as those measured on a 300 MHz NMR instrument. If a compound has two mutually coupled protons, then the coupling constant due to splitting of one proton by the other is the same as the coupling constant due to splitting of the second proton by the first. In other words, mutually coupled protons have the same numerical value of the coupling constant. For example, consider a theoretical system having the group C with HB, C with HA and HM. Here the signals due to two equivalent protons HA is split into a 1:1 doublet by protons HB with the coupling constant of JAB. Likewise, the signal due to HB is split by two equivalent protons HA into a 1:2:1 triplet having the same coupling constant JAP. Magnitude of coupling constant. The numerical value of the coupling constant depends on the number and kinds of intervening bonds, spatial positions of the two coupled protons, and the structure of the molecules as discussed below. For vicinal protons, that is, protons attached to adjacent carbons, varies from 2 to 14 Hz depending upon the spatial position of the coupled protons and the molecular structure. In case of compound in which free rotation is possible, protons with anti-conformations have J is equal to 5 to 14 Hz, while protons with gauge conformations having J is equal to 2 to 6 Hz. In compounds of the type CH3CH2X, the typical value of the coupling constant lying between 6.5 to 7.5 Hz. For alkenes, trans protons have higher J values 11 to 18 Hz than cis protons 6 to 14 Hz. For geminal protons, that is non-equivalent protons attached to the same carbon, the value of J varies from 10 to 18 Hz depending upon the dihedral angle and the molecular structure. However, for vinylic protons, J varies from 1 to 4 Hz. For allylic protons, J is equal to 2 to 13 Hz. For aromatic protons, J decreases as the distance between the two protons increases. For example, J ortho 8 to 10 Hz, J meta is equal to 1 to 3 Hz, J para is equal to 0 to 1 Hz. The value of the coupling constant is sometimes very useful in determining the structure, particularly the configuration of the molecules. Magnetic equivalence of protons. It has already been discussed that the magnetic equivalence or non-equivalence of protons is very important in PMR spectroscopy, since it determines both the numbers of signals and the splitting. Now, it has been found that magnetic equivalence of proton in some cases depend upon the rate at which certain molecules changes, such as rotations around single bond occur. Therefore, PMR spectroscopy can also be used to study these molecular changes. To illustrate this, let us compare a PMR spectrometer with a slow speed automatic camera. Suppose we want to get the photograph of the spokes of a rotating wheel with the speed automatic camera. Suppose we want to get the photograph. Clearly, the nature of the photograph will depend upon the speed with which the wheel rotates. If the wheel rotates at a very slowly speed, the photographer will show all the individual spokes quite sharply. If the wheel rotates little faster, then the photograph will show only blurred spokes. If, however, the wheel is rotating very fast, the photograph will show just a circular smear. In a similar way, if the molecular changes occur slowly, the PMR spectrometer will see the proton in each of its environments. If, on the other hand, the molecular changes occurs at a relatively faster rate, the spectrometer will not be able to distinguish between the changing environments but will see the proton in its average environment. Let us now consider the molecule of ethyl bromide. It can exist in three equally stable staggered conformations 1, 2 and 3, which are identical in all respects except that in each case, a different proton occupies the anti position with respect to the bromine atom. In each of these conformations, one of the protons, which is anti with respect to the bromine atom, is different from the others two, which are gauche. Since the three conformations are equally populated, we should see two PMR signals with a relative intensity of 2:1, but still the 3-methyl protons gives only one PMR signals. This suggests that all the 3-methyl protons are magnetically equivalent. This is due to the reason that the rate of interconversion of 1, 2 and 3 by rotation through carbon-carbon single bond is very fast. As a result, the PMR spectrometer sees all the 3 methyl protons in the same average environment, hence only one PMR signal is obtained. A similar situation occurs in case of cyclohexane molecules. It contains 12 protons, 6 of which are axial and the remaining 6 are equatorial. Since the rate of interconversion of one chair conformation into other by rotation about carbon-carbon bond is very fast, 10 to the power 6 times per second, the PMR spectrometer sees only an average environment in which each proton is half axial and half equatorial. As a result, at room temperature, cyclohexane shows only one sharp signal for all the 12 protons. If, however, by lowering the temperature we could sufficiently slow down the rate of rotation about single bonds, the PMR spectrometer might be able to distinguish between the individual environment of each set of 6 equivalent protons, and then we should be able to see two signals. This is exactly what happens. Thus, when cyclohexane is gradually cooled down, the single sharp peak observed at room temperature is seen to be broadened and then tends to split around 200 Kelvin, and finally at 173 Kelvin it is split into two sharp peaks, one due to axial proton at delta 1.2 and other due to equatorial protons at around delta 1.7. This process of broadening of signals at decreasing temperature and the ultimate splitting into separate peaks has been used for estimating the E-act for rotation about carbon-carbon single bonds. Indeed, by using this method, the energy barrier of 46 kJ mole inverse was calculated for rotations about carbon-carbon bond in cyclohexane. Now, applications of PMR spectroscopy. PMR spectroscopy has been useful in the study of organic chemistry. Some of its important applications are discussed below. Identification of substance like IR spectrum. PMR spectrum can also be used as a fingerprint of the substance. If the PMR spectrum of a given sample is exactly the same as that of a known compound, the given compound must be identical with the known compound. In this way, PMR spectroscopy can be used to establish the identity of a substance's determination of molecular structure. PMR spectrum are often very complex, but this complexity is not a disadvantage but is often useful in determining the molecular structure since it makes the spectra characteristics. Furthermore, even the complex spectra can be made interpretable by using the techniques of deuterium, labeling, and double resonance. Thus, PMR spectroscopy is increasingly being used as a versatile tool for structure determination of organic compounds, identifications of reactions products. Wherever in a reaction two or more products are theoretically possible, PMR spectroscopy has been used to identify the actual product. For example, addition of HCl to 1-methylcyclohexene can in principle yield other product. This confirms that the product formed is 1-chloro-1-methylcyclohexane. Had two products been, it would have exhibited a doublet for the 3 methyl protons at around delta 1.0. Distinction between geometrical isomers. PM spectroscopy can be used to distinguish between cis and trans isomers. The distinction is based upon the magnitude of coupling constant, that is 11 to 18 Hz for trans protons and 6 to 14 Hz for cis protons. Distinction between inter and intramolecular hydrogen bonding. During hydrogen bonding, transfer of electrons occurs from the hydrogen atoms to the neighboring electronegative oxygen or nitrogen atom. As a result, hydrogen bonded hydrogen get deshielded, the amount of deshielding being proportional to the strength of the hydrogen bond. The extent of hydrogen bonding depends upon the concentration, temperature, and the nature of the solvent. In concentrated solution, more molecules can come in contact with each other to form hydrogen bonds. As a result, in concentrated solution, hydroxyl protons absorbs around 4 to 5 delta, while in dilute solutions, the absorption shifts to higher field around 0.5 to 1 delta. The extent of intramolecular hydrogen bonding, on the other hand, remains unchanged on dilution, and hence the chemical shift of the intramolecularly hydrogen bonding hydroxyl group remains unchanged. For example, Salicylates 10 to the power 10 to 12 delta, and enol forms of beta diketones 10 to 16 delta shows OH resonance at approximately the same delta values at all concentrations. Determinations of relative amounts of tautomers, beta diketones and beta ketoesters exhibit ketoenol tautomerisms. PMR spectroscopy can be used to determine the relative amounts of tautomers in a tautomeric mixture. Let us take the example of acetyl acetone, which exists as a mixture of keto and enol forms. Its PMR spectrum is shown. Since the rate of interconversion of keto and enol forms is quite slow on the NMR time scale, therefore both keto and enol forms show signals independent of each other and are well separated. The chemical shifts of various protons in the keto and the enol forms are shown below. By comparing the relative intensities of the CH2 ketoforms and double CH group signals, it is possible to determine the relative amount of ketone and enol form. From the spectrum, total intensity of 6 methyl protons is equal to 20 units. Intensity of 2 CH2 protons is equal to 1.33 units. Intensity of 1 double bond CH protons is equal to 2.66 units. Percentage of keto form is equal to 6 up by 2 into 1.33 upon 20 into 100 is equal to 20. Percent of enol form is equal to 6 upon 1 into 2.66 upon 20 into 100 is equal to 80. Alternatively, 1.33 protons of keto form into 1 by 2 molecules protons upon 2.66 proton of enol form into 1 molecules of proton, which is equal to 1 molecule of keto form upon 4 molecules of enol form. Percentage of keto form is equal to 1 upon 1 plus 4 into 100 is equal to 20%. Percent of enol form is equal to 4 upon 1 plus 4 is equal to 80%. Study of proton exchange processes. Like conformational interconversions, some chemical processes occur so fast that PMR spectrometer cannot observe them. For example, the rapid exchange of OH protons among the molecules of an alcohol and NH protons among the molecule of an amine. To illustrate the effect of such processes on the PMR spectra, let us discuss the PMR spectrum of a simple alcohol ethanol. The PMR spectrum of ordinary alcohol shows a triplet J is equal to 7.1 Hz at delta is equal to 1.17 due to 3 equivalent methyl protons, a quartet J is equal to 7.1 Hz at delta 3.62 due to 2 equivalent methylene protons, and a singlet due to hydroxyl proton at delta 5.37. Thus, the spectrum of ordinary ethanol does not show spin-spin coupling between the hydroxyl proton and the methylene protons, even though they are present on the adjacent atoms. This is attributed to rapid exchange of hydroxyl protons between the different ethanol molecules of the same sample. This exchange of protons is catalyzed by small amount of acidic and basic impurities present in ordinary ethanol. Due to this rapid proton exchange, each hydroxyl proton behaves as if it is attached to a number of ethanol molecules. Consequently, the hydroxyl proton sees all the possible spin orientations of the hydrogens on the methylene group. Similarly, the methylene hydrogens see so many different protons on the hydroxyl oxygen, some with spin plus half and some with spin minus half. In other words, methylene proton sees only one average spin orientations of hydroxyl proton, and hydroxyl proton sees only one average spin orientations of the methylene protons. As a result, neither the methylene protons split the signals due to hydroxyl protons, nor the hydroxyl proton splits the signal due to methylene protons. Thus, rapid chemical exchanges causes decoupling. However, if all the impurities present in ordinary ethanols are eliminated, the resultant ultra-pure ethanol shows the expected triplet for hydroxyl proton due to splitting by the two methylene protons, and a complex multiplet for methylene protons due to splitting by 3 equivalent methyl protons and 1 hydroxyl proton. This is due to the reason that complete removal of last traces of acidic or basic impurities either altogether stops or greatly slows down the complete removal of last traces of acidic or basic impurities either altogether stops or greatly slows down proton exchange process, and hence coupling between the hydroxyl proton and the negative methylene protons is observed on the NMR time scale. The complete spectrum of ultra pure ethanol is shown in figure. Limitation of PMR spectroscopy. In spite of the fact that the PMR spectroscopy has been extremely useful in the structure determination of organic compounds, it has certain limitations as given below. To ensure homogeneity of magnetic field in all proportions of the samples, the PMR spectra are recorded only on liquid samples. The liquid may be the solution of the compound in a suitable solvent, or if the compound is a non-viscous solid liquid, even neat liquid can also be used. A serious drawback of the PMR spectroscopy is that it cannot be used to distinguish enantiomers of a compound. However, recently by using chiral solvents, this limitation has been overcome. PMR spectra of some molecules. To help the student in solving problems on structure determinations, the PMR spectra of some simple organic compounds are reproduced below. Ethylene bromide. The PMR spectrum of CH3CH2Br shows two signals. Triplet at delta 1.7, J is equal to 7 Hz. Quartlet delta 3.4, 2H, J is equal to 7 Hz. Explanation. Ethyl bromide contains two types of protons. The three protons of CH3 groups are magnetically equivalent and hence produce one signal. Similarly, two CH2 protons are magnetically equivalent and thus produce another signal. Due to minus I effect of Br, the electron density around CH2 proton decreases relative to CH3 protons. Therefore, CH2 protons are deshielded relative to CH3 protons. In other words, CH2 protons absorbed at a signals are in the ratio 3:2, thereby confirming that the high field signal at delta 1.7 is due to 3 methyl protons and low field signals at delta 3.4 is due to 2 methylene protons. Further, due to the presence of two protons on the adjacent CH2 group, the signals due to methyl protons is split up into a 1:2:1 triplet in accordance with n plus 1 rule, that is 2 plus 1 3. Similarly, signals due to CH2 proton is split into a 1:3:3:1 quartet by 3 equivalent CH3 protons. Further, it is found that the spacing of peaks, that is coupling constant J, within 3 lines of the triplet and 4 lines of the quartet is the same and is equal to 7 Hz. Thus, to sum up, we have CH3CH2Br, where CH2 splits into a 1:3:3:1 quartet at delta 3.1 and CH3 splits into 1:2:1 triplet. The PMR spectrum of N-propyl bromide shows the following three signals. Triplets for 3 protons at delta 1.1, J is equal to 7.0 Hz. Sextet delta 1.95 for 2 protons at J is equal to 7.0 Hz. Triplet at delta 3.45 for 2 protons at J is equal to 7.0 Hz. Explanation. N-propyl bromide contains 3 types of protons marked A, B and C. Their relative areas being 3:2:2 due to minus I effect of the bromine atom at C1. Protons are the most deshielded and hence these protons appear at the lowest field at delta 3.45 since the minus I effect decreases with distance. Therefore, B protons are less deshielded than C protons and hence appear at a higher field at delta 1.95. The most shielded are, however, the A protons which absorb at the highest field at delta 1.1. The signals due to A protons at delta 1.1 is due to 3 equivalent CH3 protons. It is split into a 1:2:1 triplet by 2 equivalent methylene protons on C2 with the J value of approx 7 Hz. Similarly, the signals due to C protons at delta 3.45 refers to methylene protons of CH2Br. It is also split into a 1:2:1 triplet by the methylene protons on C2 with J values of approx 7 Hz. The signal due to B protons at delta 1.95 refers to two equivalent methylene protons on C2. It is split into a 1:5:10:10:5:1 sextet by two equivalent protons of CH2Br and three equivalent protons of CH3 group with J values of approx 7 Hz. The PMR spectrum of isopropyl bromide shows two signals: doublet delta 1.7546 protons at J is equal to 7 Hz, septet delta 4.30 for 1 proton at J is equal to 7 Hz. Explanation: isopropyl bromides contain two types of proton marked A and B and hence gives two signals. Their relative ratios are 6:1. The 6 protons HA on the two methyl groups are equivalent and are different from the lone protons on CHBr due to minus I effect of the bromine atoms. The single protons on the CHBr absorbs downfield at delta 4.30 relative to the 6 protons which absorb at a higher field at delta 1.75. The high field signal at delta 1.75 is split into a 1:1 doublet by the lone proton on CHBr with the JAB is equal to 7 Hz approx, while the low field signals at delta 4.30 is split into a 1:6:15:20:15:15:6:1 separated by the 6 equivalent protons on the 2 CH3 group 1,1-dibromomethane. The PMR spectrum of 1,1-dibromomethane shows two signals: doublet at delta 2.5 for 3H protons, J is equal to 7 Hz, quartet at delta 5.85 for J is equal to 7 Hz. Explanations: the PMR spectrum of 1,1-dibromomethane contains two types of protons marked A and B and hence shows two signals. The relative area under the two signals being 3:1, the upwind signals at delta 2.5 is due to three equivalent methyl proton which is split into a 1:1 doublet by the methine proton with a coupling constant of about 7 Hz. It may be noted here that as compared to the signals for the methylene protons of CH3CH2Br delta 1.7, the signals are here is shifted towards downfield due to the presence of two bromine atoms on the adjacent carbon. The low field signals at delta 5.85 is due to the methine proton. It is split into a 1:3:3:1 quartet by the three protons on the CH3 groups with a coupling constant of about 7 Hz. Here also the signals due to the methine proton as compared to the signal for methylene protons is shifted towards downfield due to the presence of two electronegative bromine atoms on this carbon as compared to one and CH3CH2Br. 1,1,2-tribromomethane shows two signals: doublet at delta 4.2 for two protons which is J is equal to 7 Hz approx. Triplet is equal to delta 5.7 for one proton at J is equal to 7 Hz. Explanations: the PMR spectrum of CH2Br shows two signals. The areas underneath these signals are in the ratio 2:1. The signals at delta 4.2 is due to two equivalent protons of CH2Br which is split into a 1:1 doublet by the adjacent methine proton of CHBr2 group. The signals at delta 5.7 is due to the methine proton of the group CHBr2. It is split into a 1:2:1 triplet by the two protons of CH2Br group. Relative to the doublet of the CH2Br, the triplet of CHBr2 appears at a lower field because the carbon bearing this proton is attached to two electronegative bromine atoms. All the facts stated above may be surprised as this. Ethanols. The PMR spectrum of an ordinary sample of ethanol has already been shown. It shows three signals: triplet at delta 1.17 for three protons at 7.1 Hz, quartet at delta 3.62 for two protons at 7.1 Hz, singlet delta 5.37 for one proton. Ethanol contains three types of protons marked A, B, C and hence exhibits three different signals. The relative areas under the signals being in the ratio 3:2:1. Due to greater electronegativity of oxygen than carbon, the signal due to OH proton is most deshielded, followed by CH2, while the CH3 protons absorbed at the highest field. The highest field signals at delta 1.17 is due to three equivalent protons of the CH3 group. It is split into a 1:2:1 triplet by the two neighboring protons on the methylene group. The signal at delta 3.62 is due to the methylene protons. It is split into a 1:3:3:1 quartet by the three adjacent protons of the methyl group. The hydroxyl protons, however, does not couple. The lowest field signals at delta 5.37 is due to the hydroxyl protons. It does not couple with the adjacent methylene protons and thus appears as a singlet. It is interesting to know that the PMR spectrum of an ordinary sample of ethanol does not show any splitting of signals due to coupling between hydroxyl protons and the methylene protons, even though they are present on adjacent atoms. This is attributed to rapid exchange of hydroxyl protons between different molecules of the same samples. Consequently, the hydroxyl protons experience only one average spin orientations of methylene protons. In other words, it does the couple with methylene protons and thus the hydroxyl protons appears as a signet. Similarly, the methylene protons experience one average spin state of hydroxyl protons and does not couple with it. In other words, the only observed splitting of methylene protons is due to the three adjacent methyl group. Further, it may be noted that the presence of acidic or basic impurities catalyze the exchange process. If all the impurities, acidic or basic, present in an ordinary sample of ethanol are removed and the PMR spectrum of the resultant ultra-pure ethanol is recorded, it has shows the expected triplet J is equal to 7.1 Hz for hydroxyl proton. Similarly, methylene proton shows a complex multiplet actually an overlapping pair of quartets due to splitting by three equivalent methyl protons J is equal to 7.1 Hz and one hydroxyl proton J is equal to 5.1 Hz. It is because in the ultra pure sample the exchange process gets slowed down and the coupling between methylene protons and the hydroxyl proton is observed. The PMR spectrum of CH3CHO shows two signals: doublet at delta 2.15 for 3 protons at J is equal to 2.84 Hz, quadrat at delta 9.68 for 1 proton at J is equal to 2.84 Hz. Explanation: acetaldehyde contains two types of proton marked A and B and hence shows two signals, the relative areas under the signals being 3:1. The protons of the aldehyde group is largely deshielded by the anisotropic effect of the pi electrons of C double bond O, while the protons of the methyl groups are deshielded only by the -I effect of CHO group. As a result, the aldehyde proton is much more deshielded than the methyl protons and absorbed at delta 9.66. This signal is split into a quartet by the three equivalent protons of the methyl group. The upward signals at delta 2.15 is due to the three equivalent methyl protons. It is split into a doublet by the aldehydic protons. The entire information is discussed below. Ethyl acetate. The PMR spectrum of ethyl acetate shows three signals: triplet at delta 1.25 for 3 protons at nearly J is equal to 7 Hz, singlet at delta 2.03 for 3 protons, quartlet at delta 4.15 for 2 protons at J is equal to 7 Hz. Explanations: the 3 proton of the CH3 group attached to the C double bond groups are in a different environment than the 3 protons of the CH3 group attached to the CH2 group. Due to the strong -I effect of the C double bond O group, the CH3 group attached to C double bond O group absorbs at a lower field at delta 2.0 as compared to the CH3 group attached to the CH2 group, which absorbs at a higher field at delta 1.25. The signal at delta 1.25 is split into a 1:2:1 triplet by the two protons on the adjacent CH2 group. Since the CH2 group is directly attached to an electronegative atom, therefore the signals due to CH2 groups appear at the lowest field at delta 4.15 is split into a 1:3:3:1 quadrat by the three equivalent protons of the methyl group. All the toluene. The PMR spectrum of toluene has already been shown. It consists of two signals, singlet at delta 2.32 for 3 protons, singlet at delta 7.17 for 5 protons. Toluene has 8 protons, 5 of which are aromatic while the remaining 3 are of the methyl group. Thus toluene has two types of proton marked A and B and hence shows two signals with their relative integral areas of 3:5. The signals due to 3 protons of the methyl group ring appear as a singlet at delta 2.32 as compared to methyl protons of an alkane. The methyl proton of toluene appears somewhat downfield because of the small amount of deshielding by the induced magnetic field of pi electrons of the benzene ring. The 5 aromatic protons absorb as a singlet at delta 7.17 as compared to benzene at delta 7.27. These protons are slightly shielded and thus appear a little upfield. This is due to the weak plus I effect of the methyl group, which increases electron density in the carbon-hydrogen bond, thereby shifting the absorption to a higher field. In principle, the 5 protons of toluene are not equivalent. They can be divided into 3 types, that is 2 ortho, 2 meta and 1 para with respect to the methyl group. Since CH3 group has a weak plus I effect, for all the 5 aromatic protons experience practically the same shielding effect. Consequently, all the 5 protons have the same chemical shift and thus produce a signal which appears to be singlet in a PMR spectrum recorded by a low-field 16 MHz NMR spectrometer. It may, however, be noted that if a 200 to 300 MHz strong field spectrometer is used, the 5 aromatic protons of toluene will split up into a multiplet. Benzaldehyde. The PMR spectrum of benzaldehyde shows 3 signals, complex multiplet at delta 7.40 for 3 protons, complex multiplet at delta 7.72 for 2 protons, 2 orthoprotons, singlet at delta 9.86 for 1 proton, CHO. Explanation. Due to anisotropic effect of the carbonyl group, the aldehydic protons absorbs at the lowest field. Due to the strong electron withdrawing nature of the carbonyl group, the 5 aromatic protons are not equivalent. The 2 orthoprotons are of one kind and the 2 metaprotons are of another kind, while the 1 paraproton is of different kind. Since these protons experience deshielding effect of different extent, they show different chemical shift. The orthoprotons are further deshielded by the anisotropic effect of the carbonyl group and hence appear at a lower field, while the remaining 3 protons produce a separate signal at a lighter, higher field at delta 7.0. Further, due to different coupling constant, 8 to 10 Hz for ortho, 1.1 to 3 Hz for meta, and 0.0 to 1 Hz for para position, both the signals are split up into multiple complex. Acetophenone. The PMR spectrum of acetophenone shows the following 3 signals. Singlet at delta 2.25 for 3 protons, complex multiplet at delta 7.41 to 7.49 for 3 protons, 2 meta and 1 para protons, complex multiplet for delta 7.8 to 7.9 for 2 protons, 2 orthoprotons. Explanations. The 3 protons of the methyl group are equivalent and thus appear as a singlet at delta 2.25. The 5 aromatic protons of acetophenone, like those of benzaldehyde, are not equivalent. The orthoprotons are much more deshielded than the meta and the paraprotons due to anisotropic effect of the carbonyl group. Thus, the 5 aromatic protons fall into two groups, with the ortho protons appear at a lower further due to the different coupling constant 8 to 10 Hz for ortho, 1 to 3 Hz for meta, and 0 to 1 Hz for para positions. Each group of proton is split up into a multiplane. Para-anisidine. The PMI spectrum of para-anisidine exhibits the following signals. Broad signals at delta 3.4 for 2 protons NH2, sharp signals at delta 3.7 for 3 hydrogens in OCH3, doublet delta 6.55 to delta 6.65 for 2 protons ortho to the NH2 group at J is equal to 9 Hz. Doublet delta 6.70 to 6.75 for 2 hydrogen proton ortho to the OCH3 group. J is equal to 9 Hz. Explanation. The two protons of the amino group due to rapid proton exchange between different molecules exhibits a broad signals at delta 3.4. The three protons of the methoxy group are equivalent and hence absorb at a signal at delta 3.75. The four aromatic protons are however not equivalent due to lesser electronegativity of nitrogen than oxygen. The NH2 is a stronger electron donating group than the OCH3 group. Therefore, protons ortho due to the NH2 group, that is HA, are more shielding than the protons ortho to the OCH3 group, that is HB. In other words, A protons absorbs at a higher field, that is delta 6.55 to 6.65, than Hb protons delta 6.70 to delta 6.75. Each Hb proton is split into a doublet J is equal to 9 Hz by the Hc proton or vice versa. As a result, 4 aromatic protons shows 2 unsymmetrical doublets. The para-nitrotoluene. The PMR spectrum of para-nitrotoluene displays the following signals. Singlet at delta 2.5 for 3 protons, doublet at delta 7.3 for 2 protons ortho to CH3 group at J is equal to 9 Hz, doublet delta 8.0 2 protons ortho to NO2 group at J is equal to 9 Hz. Explanation. The 3 protons of the CH3 group are equivalent and hence produce a singlet at delta 2.5 as compared to the methyl protons of toluene. The above signal appears somewhat downfield due to additional deshielding by the other electron withdrawing NO2 group. The 4 aromatic protons are of two types. The 2 protons ortho to the methyl group are equivalent but are different from the 2 protons ortho to the nitro group, which themselves are equivalent. The 2 protons ortho to the methyl group produce an absorption signal at delta 7.3, which is split into a doublet at J is equal to 9 Hz by the neighboring proton, that is Hb ortho to the nitro group. Similarly, the 2 protons ortho to the nitro group produce a doublet J is equal to 9 Hz at delta 8.0 due to coupling with the neighboring proton, that is HA, ortho to the CH3 group. The somewhat downfield position of this doublet at delta 8.0 relative to the doublet of HA proton at delta 7.3 is due to the strong deshielding effect of the nitro group. Thank you for watching.